The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is blind spots of low voltage testing. It's being presented by Leslie Reed from Baker Instruments and Megger Company. With a BS in mathematics, Leslie was a software developer for the United States Forest Service for 12 years. She then decided to return to school to obtain her teaching license in mathematics from Colorado State University. After teaching as an undergraduate mathematics instructor for 3 years, she returned to software development with Baker Instrument Company. Having accumulated over 16 years' experience as a software engineer with Baker Instrument Company and ultimately as the lead software designer for the electric motor condition monitoring division, she again transitioned into the application side of motor testing and training. She now has over 5 years' experience as an application engineer and technical instructor, providing technical solutions and instruction across many industries around the world. We expect today's presentation to last roughly 30 minutes, and then we'll answer any questions that have been submitted. During any time during the presentation, you can send questions through the question box, which is in the right side of your webinar controls. I also wanted to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of the presentation. And at this time, I'm going to turn the presentation over to Leslie.
Hello, everyone. I'm excited at this opportunity to talk to you guys about the blind spots of low voltage testing. And the subline there of finding faults where they begin, not where they end. So we're after that reliability piece in motor testing. So as far as we do motor testing, I would consider there being 5 critical tests that should be performed in order to assess the installation integrity of the motor and its environment in which it's living in. So we're going to take a look at those 5 critical tests, the big 5 here. The first one is Kelvin resistance testing. So here we're taking resistive measurements from phase to phase and evaluating the resistive imbalance of that motor. And this is considered a low voltage test. The second one is going to be DC testing, a nominal DC testing. So this is again a test performed at or below nameplate value of the motor. And it is after looking for there is our ground wall insulation integrity. So here we're going to evaluate ground wall insulation at or near nameplate voltage. The third test is also a DC test, but here we're going to bring that voltage up higher than nameplate to thoroughly evaluate that ground wall insulation, giving us a little more information than our low voltage test gave us. So again, we're going to be evaluating that motor to voltages it sees similar during opening and closing operations of the breaker. So we're going to simulate that and see how the insulation, ground wall insulation, behaves, how it responds to that. The fourth test to take a look at is surge testing. And surge testing, the nature of how that test is performed, lends itself to finding turn-to-turn or copper-to-copper insulation issues. So we've tested the ground wall insulation, we've tested our connections with the resistance testing, and with surge testing, we're going to cover turn-to-turn insulation, copper-to-copper insulation. The fifth test, which is actually not a test as such, but a monitoring of the motor while it's running. So dynamic monitoring of the motor. We're going to hook on to our currents and voltages of that motor while it's in its normal operation environment. And we're going to take a look at the voltages and currents and then do some math, and we get a lot more information there as to the environment that motor is living in. So these are the 5 tests that I would like to take a look at through this presentation. So the first one here will be the Kelvin bridge, or the Kelvin insulation or copper testing. And the first thing we want to look at is how this test is configured. How are we performing this test? So we're going to hook up our test leads to the 3 test leads, are the leads of the motor. And then we're going to basically push a current source through the test leads and measure the voltage drop across the resistor, meaning the phase-to-phase resistance of that motor. So we're making a 4-wire measurement here. So we're going to supply the current source so we know what that is. We're going to measure the voltage drop across that resistor, and then using Ohm's law, we actually calculate the resistance of that circuit. So we're going to get 3 values from that, from lead 1 to 2, 2 to 3, and 3 to 1. So we get our phase-to-phase resistance for each of the 3 combinations. And then to evaluate that test is going to look at the balance of that circuit. So it's kind of hard to know walking up to motor what the actual phase-to-phase resistance of that motor is. And if you're testing for switchgear, that's going to include the cables. The length of the cables kind of plays into how much resistance is in that circuit, and you wouldn't necessarily know what that resistance should be. So the way we're going to evaluate this test is through the balance of each of the 3 phases. So a way that we do that is to take it into 2 methods. The first one is deviation from average. So we take whatever is the most deviation from average of the 3 values, divide by that the average, and we get an imbalance calculation there. Then we're going to compare it to a threshold. So there's 2 ways, again, as I said, to actually evaluate this imbalance. The second method is a min minus the max, or max minus the min. Divide that by average, and that also would give us an imbalance calculation. So either method is performed in the field. And basically what we're looking at is a value, an imbalanced value, that we're going to compare to a threshold. So deviation from average, generally we're at 2.5 to 3%. Max minus min for average, around 5%. And anything over that threshold, then we're going to consider that as being imbalanced and something that we need to investigate in order to correct that issue. There's actually no established standard for what that imbalance should be. It may differ a bit from switchgear to the motor itself. In fact, we're evaluating some different things there. If we're testing from switchgear, then we're going to assume that our imbalance is in that junction box. So we're going to go down and visit the junction box, open it up, and check our connections there. And looking for any kind of corrosion or loose connections there. We're also going to take our temperature that the resistance that we measure, and we're going to temperature correct it. Because as temperature increases, so does the copper resistance. So if we want to trend over time, then we're going to need to temperature correct. Typically that's at 25 degrees C. I have seen some places that will actually use 20 degrees C for that correction factor, or the temperature that we're correcting to. And it doesn't matter whether it's 20 or 25, you want to be consistent in that measurement so you can trend over time to see how that trend is going as you progress through the testing. Second test here we talked about is the nominal DC voltage test. Here we're looking at, again, the ground wall insulation. We're going to evaluate the ground wall insulation value, insulation resistance to ground. So we're going to apply a voltage. We're going to measure current. So as we measure current, there's lots of currents involved as soon as we start applying voltage to this system. So you can see the graph there to the lower right. We see as we ramp our voltage up, mostly what we're measuring is going to be charging current. So then we're going to let our voltage be steady. And again, this voltage that we're holding at will be determined by the nameplate voltage of the motor, be either at or below that. IEEE 43 speaks to recommended test voltages there, and they'll be at or below the nameplate of the motor. So as we ramp up to that voltage, we're going to get basically charging current is what we're going to see as mostly dominating the current that we're measuring. So we're going to allow time to pass, and as time passes, we don't change voltage. So our current then at that point, actually what we predominantly measure is going to be absorption current or polarization current. And we're going to let a little more time pass till we get to the end of our 1 minute. And then we're going to read that value, the current value that we're reading, At the end of 1 minute, we take that current value. We know the voltage, so we're going to take the voltage divided by our current and arrive at the resistance value. And then we're going to temperature correct that value so that we can compare it to a minimum value. So again, this test itself lasts for a minute, and if we were to hold voltage on to that and continue the test on after that 1 minute, then we move into the DA or the PI, which is basically an extended Megger test. After doing the low voltage insulation resistance testing, then we're going to raise that voltage up and evaluate the ground wall insulation. This helps us determine if it's approaching the end of life. So again, we're applying voltage here. We're going to read our current. We're stressing that ground wall insulation because that's where our differential is. We're going to hook up our 3 leads, energize that motor to all 3 phases will be at the same potential to ground. So any kind of differences there, we're able to see it because of the voltage drop. So we're looking at ground wall stresses. There's actually two methods of applying this voltage. It would be the conventional high pot, which is actually very closely resembles that of the Megger test. So just as we're going to ramp up to a higher voltage, but then we hold for 1 minute, evaluating the leakage current. The final static test, anyway, that we are going to perform will be a surge test. And surge test has the unique ability to basically deliver a nonlinear drop of voltage across the windings. And so here we have a difference between turns. We have a voltage drop between turns. That way we can strictly evaluate copper to copper insulation. It will reveal the weak in-turn insulation that eventually leads to a phase-to-phase or ground wall insulation failure. This is where we find the beginning of the end of that motor, is in that turn-to-turn insulation during the surge tests. So surge testing is going to cover the 3 failure modes of turn-to-turn. So 2 turns within the same coil. Coil to coil, that would be 2 turns with different coils within the same phase, or a phase-to-phase failure, which is a much greater catastrophic failure that we're wanting to avoid. Again, surge testing, this is a graph here of a surge test. We see the 3 leads, the red, blue, and yellow of the 3 phases. And then as we pulse this motor, it kind of rings back and forth between the winding under test and that of the ringing capacitor of the tester, and produces this type of waveform. And so what we're looking for as we raise voltage up is no change in that waveform. It may get higher, it will have, the amplitude will change, but we won't want to see any kind of shifting there that then would be classified as an erratic waveform, shifting left or right. So as we apply more and more voltage, this impulse nature of the energy that we're applying to the motor causes this nonlinear drop across the winding. So here we have our T1 connection to our T4. These represent our turns at the bottom. And as we raise that voltage up, we're getting a differential between turns. So these blue lines here kind of help guide our eyes there as to how much drop as we raise voltage up there is between turns. So this sets us up to see if there's weak insulation, weak turn-to-turn insulation. And if we see weak turn insulation, then we're going to see that waveform jump. It'll shift to the left for us. And that's our sign that we've got a turn-to-turn weakness or a copper-to-copper weakness in our windings. The 5th of the big 5 that we want to talk about here is dynamic testing. Dynamic testing is performed while the motor is operating to determine the system operating environment. So we're going to look at not only the motor, so it's not necessarily motor testing, but it's a collection between the power quality, the power that's being fed to that motor, and the motor and the load of each are evaluated. So we're going to look at power quality, the motor itself, and what the load is doing. Because the motor, all it's doing is reacting to what the load's giving it, what the load is demanding, what it's requesting of the motor. So these things that it can identify are things that lead to excessive heating and insulation degradation. So we can see issues with power quality that actually lead to heating in the motor. And if they're present, then we're degrading that motor much faster than would otherwise if we were giving it good power. Excessive loading is another item that we can see. We'll give you a load percentage. And given the nameplate information, we can determine that you're overloading this motor. And anytime you're overloading the motor accepts that. It's going to slow its rotor in order to produce more torque. By slowing this rotor, it's drawing more current to produce that torque. So again, we're causing excessive heat in that motor, and we're accelerating any kind of mechanical failures with that motor. We're putting more stress on the line components as we overload that motor. So dynamic testing does help us find those things. Helps us identify issues in the environment that are causing heating in that motor. While it does not directly evaluate the insulation, it does evaluate the environment that that motor is living in. So here we see what we refer to quite often as our insulation life curve. It's built around a 460 volt motor. So the y-axis there is breakdown voltage. So as a motor starts its life, its breakdown voltage is very high. And it brings us to note that while the motor's nameplate voltage may be at 460, we put more insulation into that motor to give us this margin, to give us some life to the motor. So it's going to start out dielectrically much stronger than what it's rated for running. So as that motor starts out, very high dielectric strength, high breakdown voltage, but then we put it to use. And we see as we put it to use, we can expect maybe some certain amount of time that it's doing well, but depending on how we're treating it and what environment that motor's living in, it's going to cause that insulation to degrade over time. And as it starts degrading over time, eventually, when the dielectric strength of that insulation system falls below bus voltage, that's when we have our catastrophic failure, which generally occurs, at 2 a.m. on a vacation day, that we end up having that happen to us. The difference between motor A and motor B in this scenario here may be its environment, how it's treated, lots of starts and stops. Is it got voltage imbalance? Is it being overloaded? Is it living in a really dirty environment? It's a coal power plant, has a lot of coal dust on it, or a cement plant, cement dust, chemical plants with a lot of corrosive gases that can erode that insulation. What environment is it living in? That's the difference here between motor A and motor B. And so to identify those factors as to why that motor is being on a shortened path, that's where our dynamic testing comes into play. It will reveal those factors. So again, the static testing being insulation resistance testing, phase-to-phase resistance, and the surge test, DC high pot, all those help directly evaluate that insulation. It tells us where on this curve it is. Dynamic testing is going to identify factors that are causing that motor to be on a shortened path. So let's take a look at high voltage testing. And what maybe low voltage testing isn't telling us. So why is low voltage testing leaving us short in evaluating this motor for reliability? So here we have a picture of a nameplate. Nameplate voltage is being displayed here. This particular motor, its nameplate's at 400 volts. So it's built to handle and designed to operate at full load with 400 volts of applied voltage there. The nameplate rating of that motor does not necessarily indicate the breakdown voltage of that insulation. So the voltage rating of the motor is not concerned with the breakdown voltage of the insulation. The breakdown voltage is the voltage above which the insulation breaks down electrically. So it will be higher, especially initially when a motor is first manufactured. As its breakdown voltage, the insulation can no longer withstand the stress across it. The resistance will actually drop to zero, and a significant current is allowed to flow through the insulation material. That's what happens during breakdown. However, the breakdown voltage is a separate rating than that of the operating voltage of the insulation. So operating voltage, the insulation is designed to withstand a significantly higher voltage. So we have to design this motor in such a way that its breakdown voltage is much higher than in the voltage of the applied motor, or the applied voltage. So there's several reasons why this is important, but the most important reason here is that the voltage stresses imposed on the winding during contact opening and closing operations can be as high as 4 times the applied bus voltage. So our motors are seeing voltages higher than what we're applying to them by the bus. If motors were only insulated to withstand nameplate voltage, they would fail almost as soon as they were placed into service due to these higher voltages that occur, voltage spikes that occur during breaker opening operations, and if that motor is on a VFD, it's seeing those voltage spikes during normal operation. So again, when we talk about high voltage, we're going to voltages high as what that motor sees during these time periods. Nameplate voltage is the voltage at which the motor is designed to operate. So again, high voltage in that case would be considered 110% higher than nameplate. That's an issue if you have too high a voltage. Too high a voltage can lead to saturation of the iron core and leads to excessive heating from the inside out. So as we apply more voltage than what the field is designed for, so a motor is designed as we apply voltage to that motor, we get that rotating magnetic field. The strength of that magnetic field is directly related to the voltage that we're applying to it. And if we're applying more voltage than is needed, at some point we will saturate the iron core, causing eddy currents and hysteresis losses in the iron core, which cause heating. On the other end, low voltage, something less than 95% of nameplate voltage, will lead to overcurrent and excessive heating. So here we're applying less voltage than that motor was designed to have. And so as it tries to turn that load, the load's demanding a certain amount of torque. And as that motor rotor, or the load demands that certain amount of torque, the motor has to supply that. It's the guy in the middle, and it really has no say in it. So the motor sees that the load there, as the load changes, it reacts to that. But if it doesn't have enough voltage to supply to have a strong magnetic field, then we have a weaker field, and it actually has to slow the rotor in order to draw more current to turn the same amount of load. And by drawing more current, of course, we're causing excessive heat in that motor. So these are things that the dynamic testing can actually identify for us. So operational voltage, again, high breakdown rating necessary to withstand the switching surges, which can be as high as 4 times nameplate. For instance, for a 460 volt motor, at the beginning of life, its breakdown voltage is 28 kV. So here's where we kind of come from those numbers. So here we see basically one slot of a stator with wire in it. The red part here is the insulation around the wire. This pink part here would be our ground wall insulation in the slot. So here's basically a cross-cut view of a slot of a motor. So for a 460 volt motor, NEMA would tell us that the magnet wire's dielectric strength, so the insulation around the wire, is going to be at 8400 volts DC. The Nomax itself, and this particular Nomax being used here, is at 20,000 volts DC. We combine those two, the 8400 from the magnet wire insulation, the 20,000 from the ground wall insulation, we have a combined strength there of 28,400 volts DC to ground. So that's where these numbers here, so that's where that motor starts in its life. It was designed to start. So we have a breakdown voltage well above our bus voltage at this point in time. But then we put that motor to use. We start it and we stop it, and we cause all heating of the motor, just the general running of it, depending on how we're loading it, depending on what environment it's seeing. Is it given good power quality? Is it not? Is it in a wet environment? Is it in a dirty environment? That's going to cause that insulation to degrade. So insulation breakdown voltage design rating is by design far higher than the nameplate. So we get a certain amount of life out of that motor. And as we're doing our testing, we're going to start trying to place that motor on this curve and trying to understand how much life is left in that motor and how reliable it can be. So modern test equipment, it has very much built-in safety measures. So vintage test equipment relied heavily upon the experience of and the technical ability of the person doing the testing. Today, modern test equipment like the Megger Baker AWA takes the guesswork out of that testing. So it has a arc detection circuit, which basically is the change in voltage to the change in time. So it takes a look at that, and if it detects that arc, it's going to stop the test. It's not going to continue to dump that energy into that fault. So arc detection, the rate of change of current. Again, the hardware is taking a look and watching current. If the current rapidly increases, it's going to trip the tester and will stop the test and not continue to dump energy into that carbonizing type of fault. Instantaneous overcurrent trip. So it has trip settings and is able to, again, stop the test if at any point it detects an overcurrent trip. And on the surge, then we also have what we call the pulse pulse EAR. We're looking for wave instability. And if that waveform becomes unstable, it trips the tester and we stop the test at that point. So these safety measures are built into the testing that weren't always there with older equipment. So common analysis of our faults, again, resistive imbalance. We're going to look at high resistive connections that can cause imbalanced voltage, imbalanced currents, higher heating in that motor. So high resistive connections can be the contactor surfaces, fuse connectors, termination crimps, loose or over tightened connections. A lot of times if you're testing for switchgear, you get a resistive imbalance, you open up the junction box and water pours out to your feet. That's an indication that you may need to revisit those connections. Could be improper motor circuit connections. So if you're testing at the motor, then it's suspected that there's improper connections internally to that motor. It may be just the error in labeling. So you've got the 12 connections coming out and the lines are mislabeled and you've got issues there. So you can find connection issues internal to that motor. Here's an example of a resistive imbalance at a paper mill. We've got a 4.7 imbalance. So they went to investigate in this particular outage and they found connections that have corrosion on it, giving it a higher resistance at that point, causing a voltage imbalance, current imbalance in that motor, causing high heat. So they replaced the connections and now they put that motor back onto a better curve. Other things that low voltage insulation testing can help us with is to understand the contamination level or moisture level in the motor. So grounding paths, there's parallel paths to ground that contamination can give us. And it would cause lower Megger readings. It may cause a low PI or DA, something less than 1.5. So the contamination is causing, actually provides a parallel path to ground, and we're seeing that affected in the low voltage insulation test. Could be surface contamination buildup, as we see these motors here, a lot of grease and dirt built up on them. The windings also. This increases, the PI increases capacitance to ground. So here's an example of a PI, two examples of PI testing. On the left, we see the graph here, very hairy looking. This is the presence of moisture that causes this. Pressure, the molecules, the moisture molecules, are dipoles also, and they're reacting to that voltage that we're supplying there. And we see that in the graph, so we know by looking at the PI whether we have moisture involved in that circuit. Perhaps that's why we're getting a low megon values, because we have moisture present. It could also be contamination, as we see in the right, not so much moisture, but the flattening of this curve is indicative of contamination. Basically, we would see this insulation continue polarizing if that contamination wasn't there, and the contamination holds it up. Again, those parallel paths to ground, so the current stays high there, even though the insulation may be polarizing. In the PI, we also see the effects of aging. So contamination and age will be indicated by a low PI or DA readings, where the insulation resistance values are not necessarily low. So here we see, over time, the progression of contamination and or age. If it's clean and dry through this period, then this is an indication of age. As we go and take data points, here we see every 2 years, and our PI values are steadily getting less due to contamination or age of that insulation. Contamination is what we first suspect. If that motor is clean and dry, then we suspect age of the insulation. Finally, here we bring ourselves to a higher voltage test. This is our indications of end of life if we're failing our ground wall tests here. At the end of insulation, a nonlinear current response exhibits itself in the leakage current. So high pot testing does not have to fail to demonstrate that insulation is reaching its end of life. So here's 2 examples of a step voltage test. These are identical motors, sister motors, if you will. The one on the left here, we see our step test, which again, the blue cyan colored line here represents our voltage. So as we raise our voltage up, we hold for our 1 minute, and we're going to take a reading at the end of that 1 minute. What we're reading again is current. So we're going to take a current reading at the end of that 1 minute, and then we're going to ramp and raise voltage up again by the same amount each step. We're going to hold for the same amount of time for each step, and then we're going to collect the current value at the end of each one of those steps. So what we expect here, as voltage changes, current will change, but it should change in the same way. If we're raising voltage the same amount, our current should change the same way. So good insulation systems way. So we see here this line that we've drawn through the end step values represents a constant resistance no matter our voltage. So whether we're down here at 400 volts or 3,200 volts or so, or whether we're up here at 9,300, our resistance would stay the same. Our insulation is good. That's the indication of good insulation. Here on the right, we see that we do have a linear response all the way through the 4th point here. And we start getting slight nonlinearity and then a bigger jump here. And then our final test voltage, we get even a bigger jump in current. So as we increase voltage, our current should respond in the same way. But on those latter steps, as we increased our voltage, our current increased more in the next step. This is an indication of insulation weakness. This test passed. It didn't trip. Our minimum megon values are still high, but it failed the nonlinear test. It's telling us that as we raise voltage up on this, at some point our insulation is becoming weaker. The other indication here is at this final step we do have instability in our current. So I would propose that the very next step would actually trip the tester at that point. So the step test allows you a little more control over when you stop the test or what you're reading there. You don't have to complete, you don't have to test the breakdown to have your information. You can see it here in this nonlinear response. Surge testing, again, we're looking for stability of this waveform as we pulse the motor under test. We get that turn to turn or coil to coil, phase to phase. We're looking at copper, possibly copper to ground insulations. If that happens on the early turns, we can see that with the surge test. So here we get an example of a surge waveform on the left. Yellow is the good waveform. The very next pulse actually caused the inductance of that system to go down, shifting the waveform to the left. So the white form is that failed waveform. And we're going to quantify that, how much it shifted here in our pulse-to-pulse EAR. So as we see this activity here, that's an indication that we're got a weak turn-to-turn insulation. And turn-to-turn insulation, a weak turn-to-turn insulation is the beginning of the end of most insulation systems. These 80% of failures, large percentage of failures occur, start as turn-to-turn. So you're finding the beginning here. And as we see in this picture, this particular waveform, it failed here as it was coming out of the slot. We can see the discoloration of the copper and the insulation there. Dynamic testing, it's going to help us, again, assess the environment of the motor, where it lives at. We're going to assess that power quality, voltage imbalance, high or low voltage. So again, we'll set parameters there, thresholds, usually set at 10% for high, 5% under for low end voltage, and voltage distortion. So especially voltage imbalance and voltage distortion are causing currents that are circulating in the opposite direction that we need them to. So it's working against that motor. So the motor actually has to slow the rotor some more in order to produce the same amount of torque that was required if it had perfect power. So that motor is going to become more inefficient, and it's going to cause higher heating in the motor. So now we're degrading that insulation at a faster rate. So the dynamic testing and dynamic motor monitoring can alert us to that. Other motor-related type issues. So we definitely have power quality that we can look at. It's usually from the connection point of the sensing point down upstream from where you're sensing from. We can also look at motor-related issues, such as broken rotor bars. Current is also, current there has energy expending at 2 times slip, and we can watch that. If the amplitude grows, it's an indication of broken rotor bars. We can look at it, efficiency of that motor. How efficient is this motor in the position that you've put it in, the application you've put it in? Not what's stamped on the nameplate, but given the power that that motor's seeing and the load that it's having to turn in the environment it's living in, what is its efficiency? So we can determine the efficiency of that motor. We can see severe bearing defects, the flapping of a belt, cavitation of a pump. Those are all going to be indication of things that we can see. And lastly would be load-related issues, again, process-related overloading, improper application design. So we can take a look at the startup of this particular motor, and it will draw out the torque speed curve of this motor and give you what NEMA design of that application. What's required by that application is my motor matching that NEMA design. See cavitation, gearbox-related issues, belt-related issues, all coming through in torque, and we see here at the upper right is a torque ripple for a cavitating pump, and we see the bursts of energy that it's having to use basically to overcome the turbulent waters that cavitation is causing. So that concludes the presentation of using the big 5 critical testing of resistance testing, low voltage testing for insulation resistance, high voltage testing for insulation resistance gives us that reliability piece, surge testing for turn to turn, and dynamic testing that evaluates the environment. So thank you, Nicole.
Thanks, Leslie. Okay, everyone, so that does conclude the presentation portion of the webinar, and we can now open it up to the question and answer session. And as a reminder, if you'd like to submit a question, you can do so in your webinar controls, which is in the right side of your screen. So I'm going to move on to the first question. Between the offline and online testing, which technology would you recommend a new testing program to start with?
So if this is the first time and first foray into testing of your motors, I would probably recommend the static testing to start with. Static testing, you need to go through and evaluate where your motors are on the lifeline there. And so here would be the low-hanging fruit for a brand new reliability program is to go ahead and do the surge test or static testing to find those issues that you currently have.
Okay, next question. Do I have to establish a baseline before any of the testing to be meaningful?
So again, this kind of course lends itself well to trending, especially if you're temperature correcting and you test from the same location each time. If you compare that over time and see the degradation, you can kind of get an idea how quickly it is degrading. But you can also do a one-of testing and evaluate where that motor is right now and get an idea where that motor is on its life curve. And if you don't have previous data, you may have data from a sister motor in the same application, same motor, and you can compare and trend those results also to kind of give you an idea. But no, you don't have to trend over time to make this meaningful.
Okay, can I test my motors from the switchgear through the cables?
So this we've asked that a lot. A lot of times it's easier to get into the switchgear than it is to break the leads at the junction box. And so yes, this kind of testing can be done from the switchgear. So now not only am I evaluating the motor, but I'm also evaluating my cables and the connections in the junction box to that motor. So you're evaluating more of that system than being just the motor. So there's issues a lot of times that occur that aren't just motor related. It may be I have cables that are running through groundwater and that's causing issues with the motor. It's not that the motor's bad, it's the power being delivered to that motor has issues. So you can definitely test from switchgear. Again, the deal with testing from switchgear is that if you fail any of these tests or see indications of insulation weakness, then what you have to do is go to the junction box, break those connections, and there you're testing the motor. And if the motor is still good, then you're suspect of either the cablings, so you can hypot the cables. You can, again, because you've disturbed that connection now, you reconnect and you may make a better connection and solve the problem that way. So next question?
Yep, next question. Could you explain what a rotor bar is?
So rotor bar. So here in a 3-phase squirrel cage induction motor, the stator itself, of course, is made up of iron with copper wire set into the slots of that wire, ground wall insulations put in, and then the wires laid in, and that would consist of what the stators consist of there. The rotor itself is designed to resemble that of what we call a squirrel cage. To me, it's more like a hamster cage. I've never seen squirrels run around, but I have seen hamsters run around, so it looks similar to the wheel of a hamster cage, where the bars on that wheel would be copper bars. And those copper bars are then shorted at either end. This allows current. Once we put this rotor into that spinning, rotating magnetic field of the stator, it induces a voltage into the bars, and because they're shorted, we have current flow, and it causes that current then to, or causes that rotor then to chase the spinning electrical field there. So a rotor bar is paramount to torque production. And if a rotor bar, and that bar cannot carry current. Current will not flow in that bar, and the rotor will actually slow a bit. And then as the other bars kick in, the general inertia of the spinning of that rotor will kick in and move the rotor forward. But there's this bit of slippage that occurs every time that bar is called upon to deliver torque. So that's why we become concerned about rotor bar issues, is because it causes higher heating in the motor, causes inefficiency there, it causes speeds and oscillation, overheating of the motor, and if they're not captured, the bars could fly off into the air gap there.
Okay, last question. In evaluating the nonlinear response of current in the step voltage test, when do I get concerned about the current doubling?
So, for one, the statement there of the current doubling, it isn't so much that the current doubles, but the increase from one step to the next step doubles. And that's kind of the line in the sand that we've drawn, that if that increase from one step to the next step doubles or more, that's an indication that you can stop the test at that point, and you now know where that insulation system is on its life curve. So the graph here, if I find it again, oh, that was it. So here, this, again, insulation life curve, this point here that's in red, that's motor fail zone. So if our dielectric strength or a breakdown voltage falls below bus voltage, we have catastrophic failure. The orange area here represents where switching surges occur, at the voltages at which switching current surges occur, and this is what our tests are designed to catch. So when we fail a high pot test or we fail the surge test, we would place the motor here, depending on which voltage at which it failed at. This would be the test fail zone. This yellow zone becomes what we're calling a nonlinear zone. So if you have that increase in current from one step to the next, that more than doubles, then that puts the motor here on the life curve. Again, depending on which voltage that occurs at, we're here what we call the nonlinear zone, which is above that test fail zone. So we're not failing tests, but we have an indication here, the handwriting's on the wall, if you will, for this motor. We know we have a compromised insulation system, and we need to instigate a switch out of that motor. So again, to reiterate, it's not that the current doubles, it's the increase from one step to the next.
Okay,
thank you.
While you were answering that, I had one person submit like 3 questions. So I'll start with their first one. How do you do insulation type of motor? Thermoplastic versus thermosetting?
So could you repeat the first part of that question again?
Yeah. I'll read it as it's written. How to determine the insulation type of motor? There's a question mark. Then beyond that, it says thermoplastic / thermosetting. Okay, so what we're speaking thereof is the type of insulation that's being put into the motor. Is it of the nature of thermoplastic, or is it a thermal setting type of insulation? There's no good way of determining that as far as writing, looking at nameplate information, it doesn't tell us that. So the biggest guideline we have for that is IEEE 43, which talks about motors made in the 60s or before the 60s having the thermoplastic type of coating. And later, motors made wound later than that would have the thermal setting type of insulation. So that's kind of our biggest guideline on determining which type of insulation. And of course, they behave differently as temperature changes. So we have a different type of equation for temperature correction on those 2 types of insulations. Second question? Second question, where should we take the temperature for the motor? Inside the motor or outside ambient temperature?
So another good question, because according to IEEE 43 that talks about temperature correction for insulation resistance testing, actually specifies that we want winding temperature. So we're trying to get the what we want to put in that equation to temperature correct is winding temperature. A lot of times that is difficult to assess. So that's where people have started, totally enclosed motor. You can't get at the windings. So again, I would establish taking temperature, perhaps in the middle of the motor, away from the bearing ends, always taking that temperature from the same spot. It's difficult to use ambient temperature unless that motor has been shut down, has been sitting at that temperature over a period of time. Then you can kind of assume ambient temperature.
Okay. Third question. Is high pot test a destructive test? How often should we do this for a 480 volt motor?
So high pot testing, high potential testing, and the one that we have been talking about in this process is a DC test. So we're performing a DC high pot test, which is considered less destructive. And in this case, we're performing that test at a much lower energy level than every time you hit the stop and start button of the motor. So consider this, that every time you're starting that motor, you're doing a high pot and surge on that motor with all the energy of the distribution system behind it. Here we're doing it at a very low current, very low energy level. And so if the winding is degraded, if we have a weak insulation, it can be destructive. But if the winding is not degraded, however, the answer is no. So no significant degradation to that winding by high pot testing. The only way the insulation will be degraded is by excessive charge flowing through the weakened material, and that's not happening with a good insulation system. However, if your insulation is degraded, then the current that flows with the arc can potentially cause further carbonization of that degraded area. And since the test is well controlled and regulated, so this is that slide we talked about, vintage instruments. This instrument in newer modern times here has the ability to stop the test before that occurs. So it's well controlled and regulated, so it minimizes any potential carbonation of that motor, thus preserving the option to continue operating the motor. So again, if the insulation degraded, high voltage testing may take away up to 1 startup cycle. So again, to realize that this high pot testing we're doing at much lower energy than that when you hit the start button. If the insulation is good, it will withstand that and report back to you a good insulation system. Whereas if it's weak, then we're reporting back to you that you have a less than reliable motor in your service. So thank you for those questions.
Yep, and thank you. That concludes our time for today. If you have further questions that weren't answered or would like to find out more about our product offering at Transcat, please contact us at 800-828-1470 on the web at transcat.com, or you can email me directly at ngenword@transcat.com. We also have a Megger store on our website at transcat.com/Megger, so feel free to visit that. That will be included in our follow-up email that will come out tomorrow or the following day. And thanks everyone for joining us today. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Thank you, Leslie, and thanks everyone. Have a great
Thank you.